Hello everyone. In this video, I wanna show you how to approximate the period of a pendulum using simple harmonic motion. Let's first think of a circular motion. So when the object is in circular motion counterclockwise, there will be the difference in the angle. Let's say the change in angle is delta theta. And the radius of the circle is r. And the arc length made by this motion is delta s. So delta s is equal to the radius times delta theta. And then we divide both sides by the delta t, time taken. The left side becomes the tangential speed, and that's equal to radius times omega, which is a rotational speed. And the direction of the tangential speed is perpendicular to the radius. So if we move this velocity vector with the same endpoint with the original velocity vector, because this is perpendicular, this angle between two velocity vectors is the same as delta theta. So that means we can think of two isosceles triangle. One triangle is made of these two radii, and similar triangle is made of these two velocity vectors. So if we connect at the end of the arrows of velocity vectors, this indicates the change in velocity delta v, and that's toward the center. And when delta theta is small, the arc length is similar to close to the linear distance between two positions. So if we compare two triangles, delta theta is delta s over radius, and that's close to delta v divided by the tangential speed. So once again, we can divide both sides by delta t. So the rotational speed is equal to the acceleration times 1 over v. So if we multiply v to both sides, acceleration is the product of v and omega. And from the previous question, omega is v over r. So, no. V is r times omega, so the acceleration is equal to omega squared times radius. And because delta v, the direction is toward the center, this is centripetal acceleration is toward the center. So when there is an object, it will have this centripetal acceleration toward the center. And if we think of the horizontal component, This acceleration also has a horizontal component. Let's say the component is ax, and we can compare this big black triangle and a small red triangle. They are similar. So that means x over r is equal to ax over a. And when we change the acceleration to r squared times radius, radius cancel. So that means the horizontal component of the centripetal acceleration is equal to omega squared times x displacement. And once again, when you compare the direction of the acceleration is opposite to the direction of displacement. So that means if we think of the direction, the sign is negative. And the restoring force is mass times acceleration. So we can have this expression for the restoring force. And because that's proportional to the displacement and the direction is opposite, that makes the simple harmonic motion. And in this case, the constant of proportionality k is equal to mass times omega squared. And let's think of the motion of a pendulum. The gravitational force will be applied to the pendulum, and we can divide this gravitational force into two parts. So if this angle is theta, this angle is also theta. So that means this part is mg sine theta. And when the angle is small, sine theta is close to just theta. And the length of the pendulum string is L. And the arc length is S. For the restoring force, once again, the restoring force is proportional to the displacement. In this case, the constant is mg over L, and we can use the previous expression for the constant of proportionality in simple harmonic motion. So mass cancel. So the rotational speed omega is the square root of gravitational acceleration divided by length of a pendulum. And with this rotational speed, the one full cycle, 2 pi, is divided by the period of the pendulum. So the period of the pendulum is equal to 2 pi times square root of L over G. That's it for this video, and thanks for watching.